Hello everyone, I am Abhijeet Singh Raina and I will be presenting our paper titled QuickProbe, through which we introduce a novel prototyping workflow that enables a user to create quick and dirty prototypes taking direct inspiration from existing physical objects. My collaborators for this work are Shantanu, Vyas, Matthew Ebert, and Dr. Krishnamurthy. To begin this presentation, I will first talk about the motivation behind our work. Prototyping is a valuable tool in promoting creative idea generation in early design. Lim et al. Noted that prototypes can be tools to explore the design space in that they are purposely found manifestations of design ideas. Gerber noted that low-fidelity prototyping affords design practitioners the opportunity to learn from failures, thereby providing them confidence in their creative ability. The efficacy of low-fidelity prototyping goes as far back as the work by Rudd et al., who noted that the key advantage of low-fidelity prototyping is in supporting the refinements in product requirements and preliminary analysis in the early stage of design. We find three broad categories of prior works in HCI and computer graphics based on virtual prototyping. In first category, user utilizes a CAD-based BIM software to generate digital prototypes which are then manufactured using rapid prototyping techniques. The second category uses spatial user interfaces and mid-air interactions in mixed or virtual reality. They either use gestures or handheld controllers, but there's no tangibility integrated into the virtual environment. Then we have a third type, which is tablet-based, where we see some tangibility because of the tablet, but the interactions are not spatial and are limited to a 2D space because of the tablet. So there's a knowledge gap in terms of how to bring in tangibility of physical objects into 3D virtual spaces. Even though we have works that overlay digital information in the visual realm over physical space, we don't see much work where tangible interfaces can be integrated with the mixed and augmented reality. The fundamental challenge we face is that achieving precise spatial manipulation in conventional virtual environment is difficult due to interactions at the arm's length. This is critical, especially for prototyping tasks where the user must focus on the creative task rather than being distracted by the lack of spatial control. To address these challenges, our approach in this work is to create a tangible interaction workflow that integrates physical and digital spaces together in order to provide spatial control to the user during the prototyping task. For this, we present a case where such control can be obtained through direct interaction with the physical objects in closed-range spaces known as the peripersonal space. To enable a smooth integration between the physical and digital spaces, we develop the idea of blended haptic feedback, wherein not only is the user able to touch the physical object, but simultaneously feel the kinesthetic feedback from the objects in the virtual environment. Now, I will explain some details about the design considerations, system workflow, and system design considerations. First, I will talk about the design context. Context plays an important role in the design process during early phase design ideation. We decided to use wireframe modeling as a tool to create quick and dirty prototypes. Prior works have used wireframe modeling to create digital and physical prototypes as it provides an easy way to generate quick prototypes during the design ideation phase. Now let's look at the system setup. The setup comprises of a haptic device capable of providing force feedback. The stylus of this device was used to create 3D wireframe models of a physical object by directly probing the physical object. The generated wireframe models were then 3D printed. Now let's take a look at the ideation workflow. So here is a video of the user creating the wireframe model by adding control points using the click of a button on the haptic stylus. While creating the curves, the user feels a kinesthetic force from the haptic stylus. And in order to stop the curve creation process, the user presses another button on the haptic stylus to exit out of the sketching mode. The user can generate closed loops if the endpoints of the curve being drawn are close to each other. The curve can also be snapped to already existing curves to create a curve network. There were three main factors which were considered while designing the workflow. The location of the action space with respect to the body is a key factor while designing the interface. We utilize the action field theory to determine the motor control afforded by the system based on the proximity of the physical object to the user. We design the interaction such that the action performed by the user are close to the body. Galligani et al. Made a note that active tool usage, which is the haptic stylus in this case, is the use in the user's peripersonal space enhance their proxemic perception, allowing for precise control of actions. The system provided three types of feedback: visual feedback through rendering of the drawn curves, tangible feedback through physical touching of object with the stylus tip, and the kinesthetic feedback by the haptics device based on the curve geometry. The goal of this setup was to enable users to do quick prototyping by using physical objects as scaffolds. We choose curve networks to model the prototypes because it offers a good representation for quick prototyping, and similar to sketches in 2D, 3D curve networks still have the ability to express the overall shape without the necessity of complex 3D modeling. We represent the curves as Catmull-Brown splines, which are basically a special case of cubic Hermite splines. There are two different types of tangible feedbacks that the user is getting from the system. First is directly from touching the physical object, that is the tangible feedback, and the second feedback is activated when the user is drawing the curve. We model this as if the user is stretching and bending a metal wire around the physical object. And now I will talk about the experiment design and our findings from the user studies. Our experiments were designed with the goal of enabling users to create quick prototypes using our QuickProbe workflow. As a result, we conducted two sets of experiments that focused on the qualitative nature of the workflow. In the first experiment, users were asked to create kinesthetic curve networks on the surface of 3D printed objects. The objective here was to observe how users created different types of curve networks on surface of the object belonging to the same class. That is, different types of computer mice and different types of shoes. The second experiment was designed to observe how users generated artistic patterns using curve networks on 3D printed objects that served as physical scaffolds. We recruited 10 participants, 7 male, 3 female, that is 5 per experiment. The participants belonged to the age group of 18 to 26 years with background in engineering and biomedical sciences. Participants had no prior experience with sketching in virtual interfaces and in using haptic devices. For our experiment 1, where participants were asked to create curves on the surface of 3D printed objects, we saw a wide variety of designs that were quite unique. Most participants made the highest number of curves for shoe 2 except for user 3, who made the highest number of curves for shoe 1. The reason for this might be due to the complex geometry of shoe 2. This might also explain why most participants spent the most amount of time creating curves on shoe number 2. The common pattern we observed was that all users started their wireframe network by creating a closed curve at the base of the physical object and then started to work on the top. For our experiment 2, participants were asked to create artistic curve patterns on the surface of 3D printed shoes. The approach taken by them had some similarities and differences. For instance, user 6, 7, and 8 used a zigzag pattern to decorate their wireframe models, while user 9 actually made multiple closed loops for their shoe 2, creating a quite unique design when compared to others. When compared to experiment 1, the number of control points and length of the kinesthetic curves were relatively higher, while the total number of curves for the object types were similar. We also 3D printed the wireframe models by randomly choosing 2 designs per participant. We used an FDM printer and each print took around 45 to 60 minutes to print with supports. The overall feedback we received from the participants was quite positive. They felt that the design activity was engaging and made them feel creative. They also felt that their final design were worth their effort. In addition to this, we also received suggestions. Some of the major ones were the lack of rotation of the physical object, no undo redo features to delete unintended addition of control points, and limited pen movement, and lack of rotation of the drawn 3D wireframe model. That concludes all of our findings. I'll now talk about the limitations and future direction of our work. Our study reveals some important design considerations for future systems. Since the objects used as scaffolds were not tracked in the physical space, the user could not rotate them to manipulate the view, change orientation, and draw on the bottom part of the shapes. Another limitation of this system is that the visual space and action space are not co-located. In future systems, we would like to render the kinesthetic curves directly on top of the physical object, or render the physical object in the virtual display in order to co-locate both these spaces. With regards to system workflow, an editing mode is required so that the user could edit the existing 3D wireframe network prototypes and define them as desired. Thank you for your attention. For more details about our work, please read our paper on the ASME website.